today's keynote, this morning's keynote, when I first started here about 15 years ago, we were trying to build spacecraft, and we vied to do that with the MMS missions, and we were unable to, but we did take a big part of that mission. Fast forward to 2015, we launched our first 8 satellites, the Cygnus mission. And since then, Punch is our next venture into small satellites. Our keynote speaker today is the primary principal investigator for this mission, the Punch mission. Please give a warm welcome to Craig DeForest.
Terrific. Thanks, everybody. It's great to be here. When these kind folks asked me to give the keynote, my first thought was, well, I don't know that much about flight software, right? Here I am talking to the experts. But I'll be talking about the science of Punch and how flight software has affected it, which I think is an important thing to remember, both that what we write in terms of the software on the spacecraft and on the ground for our missions is a critical part of the mission. And so I want to take you on a little tour of the science that Punch will do that is enabled by the flight software and talk about some lessons learned from other missions that we're adopting into the Punch software chain. So bear with me, this is a science perspective on flight software. So we're going to start with a tour of the science, and I want to set Punch science in perspective. Punch is a mission to image the solar wind around us, and it really is right here. It's part of where we live in the environment of the solar system. So we're going to start right here where you are. You saw an aerial photo already of Southwest Research Institute. This one was taken, I think, from orbit. So that's you. Here's a scale of 1 mile. We're going to zoom out a little bit to look at the phenomena that Punch will be going after. If we zoom out to about 80 miles, that's about, you can drive that in a couple hours from here to Austin. That's sort of a human scale. Not particularly remarkable, except that, well, maybe you folks drive that every day if you have a long commute. Moving a little farther out to 800 miles, we got Texas. There are 3 major metropoli. There's San Antonio and Houston and some other place just a little north of Waco. So that's 800 miles across. That's about the size of a college road trip. So if you've been to college, or even if you haven't, you've probably taken a road trip that's about this long. Take you a day and a half to drive it. If we zoom out a little more, this is Texas in the context of the sun. So this is a swirling mass of material on the surface of the sun. What you're looking at is something called granulation. And you may not have seen it before, but this is what grows the vegetables that you eat every day. This process brings hot material from the interior of the star up to the surface. It rises just like warm water in a pot on the stove. These bubbles of hot material rise to the surface, spread out, and on the surface, they radiate into space. That's the sunlight that illuminates your house every day. And these convection cells that bring this material and this heat up from inside the star are about the size of Texas, as you can see. They reach the surface, spread out, and sink in about 5 minutes. This is a 30-minute loop you're looking at here of one of the highest resolution movies of the sun ever made. You can see this is a violent process. In about 5 minutes, these material waves sweep across the width of Texas. And it's happening at 1 million locations across the sun every day, every moment. Right now, it's happening right now. You can see, again, 2 of the metropoli are labeled there. I couldn't get the Houston label in. If we zoom out a little more, what the heck is that? Well, next to Texas is a sunspot. Who here has seen a sunspot before or heard of one? All right, most people. So you know, our star has a magnetic field. The magnetic field is very complicated. And because it is made of hot ionized material, the field is sort of concentrated into ropes in the deep interior of the star. When one of those buoys up to the surface, the field lines penetrate the surface of the sun. And that leaves a magnetized region. It's very highly magnetized. It's almost as strong as a refrigerator magnet, but a really big refrigerator magnet. Let's get a better sense of scale. So that's the Earth, about 8,000 miles across. The sunspot down below is magnetized. That prevents that lateral motion that's necessary for convection to happen. So material from the interior of the star comes up to the surface, starts to cool off, and can't move sideways to make room for more. And so it just sits there and cools off. So that dark region there is about 2,000 degrees cooler than the surface of the sun. It's hot enough that if some of it were here in the room with us, we'd say that's pretty bright. But compared to the star itself, it's dark, and so we see it as a spot. Zooming out a little more, now we're about a factor of 30 farther out. Instead of 8,000 miles across, we're looking at 240,000 miles. There's the Earth next to a sunspot. That's an actual sunspot that was on the sun just a few days ago. Temperature of the surface is labeled down in the corner. It's about 6,000 degrees. If you look very closely at this scale, you can see that patchwork of convection cells on the sun. This is not a movie, it's just a still. But they're all over the sun. There's about 1 million of them. Hopefully this is giving your brain a chance to expand if you've had enough coffee as we move out. Let's keep going. So now the size of the sun is 865,000 miles. So it's about 100 times the size of the Earth. You can fit 1 million Earths inside the sun. There's that sunspot. I stopped drawing the Earth just because it's too small to really make a big difference. If we zoom out just a little more to 1 million miles, this is what the sun looks like at a scale of 1 million miles. Now, up until now, we've been looking at visible light, either of the Earth or of space. This is ultraviolet light. You can't see it from the ground. Looking at the sun in this band of light, it's like trying to see the stars from inside this room. The atmosphere absorbs it, so there's effectively a roof. But in this temperature band, or in this wavelength band, you only see material that's at sort of 1 to 2 million degrees centigrade. So this is much, much hotter than the surface of the sun. I'm going to ask for a show of hands again. How many of you saw the eclipse just a month ago? Almost everybody. That's wonderful. That is the hottest thing you are likely to ever see with your eyes. It's about 2 million degrees Celsius, 1 to 2 million degrees Celsius, or 2 to 3 million, or 1.5 to 3 million degrees Fahrenheit. And I guarantee if you see anything else that hot, you're not going to remember much else for much longer. So anyway, this is the atmosphere of the star. It's much hotter than the surface. Why it's that much hotter is something that, we formed an entire field of science around that, trying to understand that very question. And you can see here, it's much more structured. The corona, the atmosphere of the star, is much more structured than the surface. There are loops and crazy things going all over the place, and it's getting brighter and fainter in time. This is a result of the magnetic field. What you're seeing is the remnants of titanic electric currents that are induced by that changing magnetic field. Those electric currents heat the material by processes as yet unknown, and also shape it, very much like iron filings if you played with those in elementary school. So that's the corona. We're not done yet. If we moved out, if you had really great eyes, you might have seen something like this last month. This is not the corona from last month. This is from about a year ago. There was another eclipse down in Australia, and a lot of folks use that to warm up for the present eclipse, but also just made measurements because it's another eclipse that you can travel to. You can see the chromosphere. If you saw those red spectacular prominences sticking out during this eclipse, you'll recognize what those are. You can see the structure extending out into the star field. This is a composite image for a better dynamic range. Down on the lower left there, you can see a coronal mass ejection. We'll talk more about those in a moment. That's what they look like on the sky. We didn't happen to have one going on during this last eclipse, but they are there, and they happen all the time, and they affect us. If we zoom out a little more, now we're at 24 million miles. There's the sun rendered in the middle. We're looking at white light from a coronagraph. That is an artificial eclipse, an instrument that makes an artificial eclipse in space. Punch is one of those. I'm going to get to Punch sooner or later. I will call to your attention, this is a heavily processed data set. What you're looking at here is, yes, white light that came from the sun, but it's in pseudo color. It's not really brown, it's bright white. And a lot of layers of background and noise have been stripped away from it. So this is the deepest field image of the outer corona that that has been made. So it's the deepest field that you've ever seen. What I want you to see here is that all the way out, even pretty far from the star, it's very highly structured. The magnetic field of the sun prevents the material from traveling sideways on its journey away from the star, but it is so hot. This material is so hot, it is not magnetically confined. Sorry, it's not gravitationally confined. Near the surface, it's magnetically confined, but out here, farther from the sun, the material is free to stream out into space, and you can see that it's doing that. So our star is losing mass all the time. The outer reaches of the corona are streaming out into the solar system continuously. If we subtract the overall image, we can see the differences. That allows us to see the features that are moving out through the corona. And this was very surprising. We've known about the solar wind for a long time, ever since the 1960s. But people think of it as a steady flow, perhaps with features in it. And when this movie was first made, we were so astonished to see this. We called it a riotous torrent. The solar wind is extremely variable. It is not a smooth flow, perhaps with features embedded in it. It is the features all the way down to the smallest scales we can see. So very remarkable, very complicated, and we live here. This stuff is sweeping over us all the time. If we move even farther out, now we're 50 million miles across. Okay, so that's about as far as an airline pilot might fly in a long career, be 50 million miles. That is, now you can see the outer edges of the corona. If you have kids, your kids probably know how to draw the sun. Every kid does, right? You draw a circle, you draw rays coming out. And we saw just a moment ago, when we looked at the corona, well, you can see it over on the right. You can see those rays that your kids draw. Now, with this movie, you can see how far they're supposed to go out. What happens a little farther away from the sun is, whoops, I thought I had some markup on here, but I don't, so I'll just call it out. Let's go back. There. Down near the base of this outer region, right near the label, 50 million miles, you can see the remnants of those striations, the radial lines. But over on the left-hand side, on the largest scales, you can see that they have faded out. That is a real effect. That's not something that's just in this movie. Those streams of material coming out from the sun are breaking up, just like a turbulent flow coming out of a nozzle or like a stream from a squirt gun, and they become turbulent. So even though interplanetary space, and here at 50 million miles, we're talking about interplanetary space, even though it's full of what we would call nothing at all, there's only about 10 to 30 atoms in a cubic centimeter of it. So not much stuff at all. It still acts like a turbulent fluid, even though none of the atoms ever hit each other. It's really remarkable. So that was a smooth day. This is a not so quiet day in this region. This is what a CME looks like at these distances from the sun. That's a coronal mass ejection. That's a lot of material that's ejected all at once by magnetic forces when the atmosphere of the sun becomes unstable. These things are sweeping out across the solar system, and they do impact the Earth. They cause space weather effects, if any of you are familiar with that. They're also very complicated. As you can see, these are not large, simple clouds of material like you'd expect from an explosion here on Earth. They are very complex, and they're structured by the magnetic field that gave rise to them. In the background there, you can see the stars. Those are actually remnants of the processing. The material you're looking at here is about 1/10 as bright as the star field. So if the images were not processed, you wouldn't see anything at all. You'd see an overall haze from dust orbiting the sun, and you would see the star field. This material is well under those backgrounds. So the corona doesn't really end. We're going to zoom out a little bit to look at some data from the STEREO mission that's in heliocentric orbit. STEREO A launched ahead of the Earth. It's a little bit inside our orbit, so it takes a little less than a year to go around, and it was designed to look back toward the Earth as it left. So these are some images from that as a composite of several different instruments. So as we zoom out away from the sun, that's the field you just saw. We can get all the way out to 90 degrees around. It's hard to fit all that on one screen, so we go to polar coordinates. So here in polar coordinates, the surface of the sun, instead of being a circle, looks like a vertical line over on the far right. Just to get your bearings there, the brown material in the middle, or the orange material, is the corona. And then these two gray fields out here are what we call heliospheric imager fields of view. They're quite far from the sun. So here on the left, you've got a scale that's angle around the sun, as seen from STEREO A that was ahead of us in orbit. Looking back, and you've got this logarithmic scale and radius that allows you to see all of these features at once. What I want you to see is we got magnetic systems in the ultraviolet field down near the sun there that go unstable and launch material, and it sweeps all the way across the solar system, sweeping over the planets, and then ultimately, here it comes, impacts the Earth. We have spacecraft near the Earth that can measure these features. So here you're seeing a movie of, it's going to come around one more time, a system over on the right on the surface of the star that explodes, hurls material across the solar system, it sweeps past Venus and right over the Earth, almost 90 degrees from the sun, as seen from this spacecraft. So these are things that really affect us. This event corresponded to aurora that was seen, and a geomagnetic, didn't rise to the level of a geomagnetic storm, but there were geomagnetic effects. So it changed the magnetic field of the Earth as this material was deflected around us by our own magnetic field. All right, so this is, now we're into the topic of space weather, right? So I promise you we'll loop back around to what Punch is doing. Space weather is the science of what these kinds of events, like that large CME, do to the Earth when they impact us. So I'm not going to go through every detail here. This is a slide that came from NOAA. NOAA operates the Space Weather Prediction Center. And they're very concerned with how these events on the star can be predicted so that we can predict and forecast space weather here in the vicinity of Earth. CMEs are very complicated. I called that out before. I just want to highlight that with a still here. Over on the left is a frame from that movie you saw on a not-so-quiet day. Over on the right, we've enhanced that a little bit with some unsharp masking to bring out detail. And you can see that this is really a very complicated structure. There are remnant things, that erupting writhed core, which I'm not going to talk about at length, is a remnant of an actual magnetic structure that was in the corona. It's surrounded by complicated stuff, and then there's a leading edge that's material that piled up in front of the CME. As these things come out from the star, they sweep up material like bugs on the windshield of your truck as they come out through the solar system. So again, very complicated system that we'd like to be able to understand. We finally got to where Punch is. Punch is a wide field imaging mission. Our intent is to unify understanding and imaging of the corona and of the heliosphere. That's the material that fills the solar system and constitutes what we used to call the void between planets. So we have 4 spacecraft. The reason they all work together, they They fly, well, they will fly. They're all right now in a clean room here in this, on this campus. But they will fly in a sun-synchronous orbit over the dawn-dusk line. So the sun-synchronous orbit precesses once per year, and that keeps the satellites over the same local time. So they'll be going over the dawn-dusk line as they orbit. The reason we have 4 of them is we wanted to look at these very wide fields of view as material leaves the sun and sweeps out over us. And we had to get close to a ground station so that we could downlink the data we collect. But that meant there was a ruddy great planet in the way. So we had to spread out the instruments so that we could see around the planet. We have 2 kinds of observatory. There's one coronagraph that's a telescope that looks near the sun. Telescope is a strong word, maybe a telephoto lens. It has a field of view that's about the size of the constellation Orion. So if you've ever seen Orion, that's our field of view. And it's got a very complicated bit of metal right in the center to block out the sunlight itself so that we can see the fainter stuff around it. Over on the right, we have 3 wide field imagers, which you might catch me calling WIFI. We've only recently started calling Southwest Research Institute SwRI. So this is the NIFI and the WIFI Observatory. And that's a very similar instrument, but in a different geometry. We've got a horizontal grating there. That's that gray piece on the front of the instrument that forms a horizon. And so the front of the instrument with the solar panels, or the front of the spacecraft, is in the eternal noontime of space. But that little green pocket in the back of the drawing there is a camera that is darker than the darkest night on Earth. So there was a great deal of engineering that went into designing the hardware to make that happen. This is how they work together. You can see some constellations here. That orange square on the star field is the field of view you just looked at of material coming out from the sun. These are our fields of view and how they interlock. So as the spacecraft orbit, every 4 minutes, we take a complete image sequence synchronized by GPS. So everything is within 1 second, even though they're on opposite sides of the planet. So these blinks represent 4-minute image acquisitions. And then as the spacecraft orbit around, they rotate to keep the Earth underneath them. And this trefoil field of view cycles around the sky. On the ground, we reconstruct images that aren't rotating and deliver maps of what's on the well, daytime sky. I almost said night sky because of the stars. So that's how it works. This is our launch profile. We animated this a little while ago, so the launch vehicle isn't correct, but the mission profile is. Shortly after we launch into the target orbit, we eject the 4 observatories in pairs on springs. Now, if you were to start walking right now and never stop and walk in a straight line, in 120 days, you would get a third of the way around the planet. And so these spacecraft are ejected with springs at about a walking pace. And relative to each other, they spread out over the course of 90 days all the way around the planet. So you saw right after deployment, we get the solar panels out so that they have enough juice to keep going. And then about 30 days out, after we've done basic spacecraft commissioning, we open the doors to the instruments. Those are there to protect them from dust and from contaminants during launch. But once they open, of course, they stay that way. And then we have 60 days. We do 30 days of commissioning of the instruments, and then 30 days of commissioning the entire fleet as we drift around to our relative positions. Once we get there, we have little thimble-sized rocket engines that just impart a tiny kick to each spacecraft and stop that drift, locking them in place. And at that point, they go into full science mode, where they just orbit 120 degrees apart. Every 15 degrees of orbit, they rotate to keep the Earth underneath them. 30 degrees, excuse me. And there you can see the whole constellation working together. You saw the map on the star field. This is looking back the other way, seeing how the fields of view interact. So it's beautiful orchestration, and of course, flight software enables that. This is what our field of view looks like relative to things you've seen. One of our co-investigators took this picture in 2017. There's some houses and things underneath an eclipsed sun. And this field of view is 90 degrees across. So to give you a sense of, just putting it in perspective, that's from the horizon to the zenith, right? So as a whole, we are not a telescope. We are a wide field imager that is viewing things that literally are sweeping over us. They're part of our environment where we live. These are the instruments themselves. This is a picture of the narrow field imager coronagraph undergoing test on the right and just before delivery on the left. So pretty neat to see. It's now here being integrated with a spacecraft. This is the wide field imager, what it looks like. That image on the right there is the inside of a vacuum chamber at the Naval Research Laboratory in Washington, D.C. This baffle reduces stray light so much that you can't test it in the air, because the Rayleigh scattering, the same effect that makes the sky blue, in your laboratory is about 4.5 orders of magnitude brighter than the baffle itself. So we had to pump it down in a vacuum chamber in order to demonstrate that we're attenuating stray light by 16 orders of magnitude. So that's not bad for something that's less than a meter across. We're helped by the fact that light doesn't like to turn corners. This is something that I am inordinately proud of, even though it wasn't me, it was the team that did this. This is our first light image through a punch spacecraft. This was taken in a clean room just across the campus the other day. There's some proud team members there. And that's a picture taken with the actual camera that we'll be using to photograph the solar wind in about a year's time. This is a picture that I took on Saturday of one of the spacecraft undergoing shake test. So you can see there's our integration lead, Tanya Brody, in the back, and someone inspecting the spacecraft, which is wrapped up. But these are small things. They're, you could hold one in front of you. All right, so all this stuff, I mentioned that briefly that the corona is kind of faint compared to some of the other background sources. I want to call that out. You've probably seen pictures like this in the news or on the web if you're interested in this kind of thing. These are images from the SOHO mission, where I got my start 20 years ago, still going strong. These are taken from a spacecraft that is 1% of the way to the sun from us. It's hanging at something we call the Lagrange point, which is a gravitational balance point between the Earth and the sun. They put it there because that way the planet doesn't get in the way, and you can image the sun 24/7. So these are coronagraph images of a CME, a coronal mass ejection, coming right at us back in 2015. If you're old enough like me to have seen the original Star Trek series, there was an episode called The Balance of Terror, where the Romulans fire a weapon at the spacecraft or at the Enterprise, and the Romulan weapon, you can tell it's aimed right at them because it just gets bigger in the view screen. This always reminds me of that particular episode. These things, it's coming straight at you. And it did impact the Earth. It did cause aurora. You can see constellations in the background. It's sort of fun to track. But that's after background subtraction. On the left, that's what a LASCO image looks like before we process it. There's that haze that you're seeing is a mix of stray light from the sun and actual background from dust that's orbiting the sun. So there's another kind of visual corona called the F corona, or Fraunhofer corona, that's made of this dust that's orbiting the star. We live in the middle of a dust cloud, and we don't care so much about the dust. We want to see this coronal material that's made of ions and electrons. So over here, I keep wanting to point. I think I can point here. Yeah, there we go. This is 0 to 10,000 counts in this instrument, and over here, the actual data is 1.5% of that. So it's a background subtraction problem. So I'm going to walk you through what we have to do for the wider field images, just to give you a sense of why, what we have to go through to make this stuff visible. This is the data sequence that for the outermost field of view in that Sun to Earth movie you just saw. These are 2-hour exposures looking back toward the Earth with a wide field camera on stereo. Those 2 vertical stripes are those are planets being so bright that they overwhelm the detector, and electrons spilled across the detector vertically. The planet on the right is Venus. The planet on the left is the Earth. Just left of the Earth, you can see a little dark piece of metal that was designed to block out the Earth so it didn't do what it's doing. Oops. But you can see that dust cloud I was talking about, sort of a lenticular dust cloud. If you're very keen-eyed, you can see the constellation Pisces in the upper left of the image. Look over at the brightness scale on the right. That's counts per second. So you're looking at a movie of 2-hour exposures, and the motion of the star field is from going around the sun, about 1 degree per day. And we're looking at 30 counts per second. Now we're going to start stripping away layers. So the first thing we do is treat each pixel in this movie as a time series and just subtract the minimum value. If you do that, you get this. Now, it looks like there's a lot more stars. That's because we've zoomed in on the dynamic range. Instead of 0 to 30, we're now going 0 to 1. You can start to see the point spread function of the instrument. There's like a little halo around each of the planets. That's a little bit of stray light in the lens is scattering around and causing the planet to look a little bigger than it is. You can see a lot more stars, right? It's stars all the way down. And so the fainter you go, the more stars you see. You can start to see, if you look very carefully over on the right, a little bit of motion on the right-hand side. That is the signal we're looking for, but we're not deep enough yet. So the next thing we have to do is remove the star field. So we can do the same trick. We take this movie, we resample every frame very carefully using photometric resampling to freeze the stars. Okay, now pixels on the detector are moving across the field of view, and the stars themselves are fixed. If you look, I will point it out right around here. There it is. Right above the cursor is the planet Uranus. And you can see as the movie loops around, where is it? I just lost it. It's very subtle, but when the movie jumps, it's easy to see right there. That little tiny moving dot is a planet. But when the stars are fixed, we can now subtract them. Now, it's easier said than done to do this. It took us about 1 year of research to figure out how to do this with enough photometric accuracy that we could do the next step, which, get ready, bam. When we subtract the stars, you're left with residual. You can start to see the motion. This bottom to top gradual motion is leftover from the dust cloud. As the spacecraft orbits the sun, the dust cloud moves slightly in the field of view. And so we subtract it, treating it as a constant, and we're left with this sort of residual that goes from bottom to top. The stars, we're so deep inside the dynamic range now that the stars have left statistical residue on the detector. That's those little horizontal stripes you're seeing everywhere. Those are places where a star swept across the field of view, and there's a residue in the statistical properties of the remaining pixels. Our dynamic range is 0 to 0.1, so we're 300 times inside the original dynamic range. Now you can start to see the stuff. Okay, we can try and remove that. Again, this is about as far as you can get with per pixel analysis. We have to start using image structure after this. But now you can start to see, yeah, there really are solar wind features here. If we go even one step farther, we're at 0.03. So we're a factor of 1,000 inside the original dynamic range. No, factor of 100. 30.3, yeah, factor of 1,000. We can use Fourier analysis. We Fourier transform the image, and that allows us to eliminate things that aren't moving the way the solar wind moves. The Fourier transform is a mathematical transform that it spreads things out that are localized in space, but it localizes things that are moving. And so we can use that to remove things from the movie that aren't moving and then transform back to real space. So we did that, and now you can see that is a coronal mass ejection crossing the field of view. There's some ringing artifacts if you look closely, so we do some batch processing to get the ringing to cancel out. This is back in solar observing coordinates. We've gone back from the celestial frame back to the detector frame. And here we average across batches. So you'll see little jumps here as we bring different batches in. Now you can see the solar wind, right? And it's 1,000 times fainter than the original dynamic range. So that's pretty cool. But we have to do that routinely with punch. So I want to look at some of the things in this movie that aren't quite right because we want to fix them for punch. The first thing is you can see there's an old-timey look here. It sort of looks like an old hand-cranked movie. It's getting brighter and fainter. That is a real effect. That is partly from the mechanical shutter of the instrument, but it is partly from jitter in the flight software. Stereo was launched 15 years ago, but it does have a real-time operating system on board that's doing multitasking. When we go to a multitasking operating system, we accept phase jitter in all of our timing, right? Because it takes time to interrupt. And that phase jitter is introducing a 0.1% variation in exposure time. And we can partially but not fully correct for that. And so that is what you're seeing over on the right. That is the effect of a multitasking operating system on board your spacecraft. We have telegraph stars. Those are those little blinking spots. Those are caused by nonlinearity, which is not nonlinearity in the detector. It is induced by onboard processing. These are 2-hour exposures. What I didn't mention and what you didn't see is cosmic rays. The 2-hour exposures are accumulated through several, well, the dozens of camera frames. And the fact that there's a time series of camera frames allows the flight software on board to do cosmic ray removal. It looks for spikes in the time series of each pixel. But there's a subtle statistical effect which causes, in bright stars, the brighter the star, the more photon counting noise there is. So bright things are noisier. And so with any detector, you have to balance false positives and false negatives. And so the bright, noisy pixels have more false positives for spike detection than fainter pixels. As a result, there's an ever so subtle nonlinearity in the response of the system. The detector itself is just fine, but by the time you impose this onboard cosmic ray removal, you've got a nonlinear detector. It's nonlinear at the 1% level. And that's enough that the stars come through, but they're everywhere. Remember, the brightest stars are just a few, but there are stars everywhere in that field. We did the analysis. The flight software is the largest noise source from these two effects. It's 10 to 30 times brighter or more higher amplitude than the actual photon noise that limits the instrument. So this is a case where being a little more careful in the design, we didn't know this, right? This is a great instrument. I love this instrument. On the other hand, if we knew then what we know now, we could have designed the flight software to not do these things and gotten even better measurements. So for punch, we're regularizing our exposure time. We don't have any mechanisms to regulate the exposure. We're using frame transfer on the camera that gives us electronic precision in the timing. But more importantly, we've moved the exposure timing into the FPGA so that it's not a multitasking operating system. There's no jitter effectively in the timing. We don't de-spike on board. We're going to download all our spikes and deal with them on the ground where we can address those nonlinearity effects more precisely because we have more resources on the ground. I want to highlight why that nonlinearity is a problem. If we have a pixel grid and the star is moving across it, stars are very tightly localized. And so if the star happens to line up with the grid, all of the photons from that star land in one pixel. So that fills the well on that pixel. And in a detector, there's a real effect. Most detectors that are nonlinear get lower gain when they saturate. If you anti-align the star, if it lands on the boundary between pixels, you spread out that light over 4 pixels. And as a result, you're down in the linear regime for most detectors. Now, this detector does have great linearity. And so at first, we thought that was what was causing the star print through. But as it turned out, it's not the detector. It's this business about the more and less noise. And this is just what I just said before, that we have spike removal on board because of the inevitable trade between false positives and false negatives. That greater noise means that we get more false positives in stars that happen to be centered than the same star when it's on 4 pixels. That makes it hard to remove that as a background, at least to the precision we need. So for punch, we have to compress our data. Almost everybody does. We have about 1820 gigabits per day is our data budget. Our raw science data volume is 85 gigabits per spacecraft per day. And that's because we're making an image almost every minute. I mentioned a 4-minute cadence, but we're taking polarization sequences in that time. And a polarization sequence takes 3 images. We also, in between each of those, we take a clear image to test the polarization processing. So it's a lot of data. So we have to compress the images about 5 times. We don't want to use lossy schemes because, as you saw, we have to be exquisitely careful about the photometry. So to do compression, we're masking out the detector, we're doing square root coding, and we're using an actual lossless algorithm. And I'll talk about those things briefly. Masking is the best compression ever. Don't downlink what you don't want. So these are our fields of view for the different instruments, the NIFI on the left, the WIFI on the right. The gray areas are regions of the detector surface that we're not using. And so we actually don't get rid of them, but we rely on the downstream lossless compression. We just set those to a fixed value. Fixed values compress extremely well. So instead of downlinking detector noise and offset, we're downlinking a constant value there. We don't care about the constant value, but we do know that later on it will compress extremely well. So we get 25% data for free. So down at the bottom there, you can see we're compressing 1.33x just by throwing away the parts of the image we don't want. And that's a simple masking operation. We have a mask image on board. Any place the mask is true, we just set the data to a constant value. The next thing is we square root code. I don't know if you've encountered square root coding before, so I wanted to talk briefly about it. If you count n things, you in general take up an error that's proportional to root n. And so when you count photons, you incur noise that is proportional to the square root of the number of photons you counted. In absolute terms, the noise grows like the square root of the value. But in relative terms, of course, it shrinks like the square root of the value. So if you're downlinking linear data and you're collecting numbers of things like photons, you're actually over-precise at the bright end of your spectrum. You are bright end of your dynamic range. You're representing with a full 16 bits a value that has maybe 8 bits of noise on the bottom end. And so that's doubly bad because on the one hand, you're over-representing your data. So you're downlinking bits you don't need to downlink. And 2, the bits that you are downlinking that are extra don't compress, right? Random signals, random numbers are precisely the kind of thing that doesn't compress at all. And so you're making your algorithm worse at the same time that you're overloading the algorithm. So what we do is we represent our image not with a value proportional to the photometry, but with the square root of that value. And so that introduces a coding error because the coding is more granular toward the larger end of the dynamic range. But we've made sure that the coding error is underneath the noise floor of the data. So on both of these plots here, you've got an orange line that represents the noise level of a particular data value. The data values are plotted across the bottom of the plot. And the blue line shows the error incurred by square root coding those data. You take the square root of the value scaled to a certain number of bits, and that gives you a little bit of error relative to the original data, but it's well inside the actual noise. And that does two things for you. One, it means that you don't care, but two, it means that the noise itself dithers. So if you've done signal processing, you know that dithering across digital transitions is important. And so the photon noise itself dithers the square root coding. This is actually kind of a common technique. It's been used since the 1970s, at least. But we took kind of a deeper dive into it. Oops. We took some existing data, we square root coded it, we decoded it, and looked at the difference. And over there on the left, you can see a close-up of one of the coronagraphs that I just showed you data from. Over on the right, you can see the difference between what happens to those data before and after you square root code it. You see any stripes in there? Yeah. A stripe means that the square root coding is introducing error, even though I just told you it shouldn't. Dang. So it turns out the problem is not with our code. The problem is with the operation of a square root. If you do integer arithmetic, it's nonlinear. And so the square root over and underestimates each value a little bit, and the amount of over and underestimation changes across the number line. And so the purple line on this plot here is the column average, and it doesn't matter. It's the error that you incur by coding and decoding just using the square of an integer number. You take an integer, take the square root of it, then on the ground you square it again, and you find the average value for several 100,000 iterations. What you find is this variation right here. In output, the mean value of the output with a noise applied varies by about half a dn, half a count. Well, half a count shouldn't matter, except for something like what we want to do with punch, where we're imaging exquisitely faint signals against a bright background. It matters a lot. So we actually developed a Bayesian inversion to this, where the inverse of the square root is not the square, it's the square plus a small correction factor that depends on the integer arithmetic. So when we apply the Bayesian inversion, over on the left is what you just saw, over on the right is after we do this sort of more subtle inversion on the ground. So pretty pleased about that. But this is another example where when you're really drilling down, if you just use a technique that you know should work, it doesn't necessarily work to the precision you need. And then we use JPEG-LS. JPEG-LS is tested on, it's a commercial algorithm. It exactly reconstructs the original image. We've tested it on star fields. We get 2.8 to 3.3 on 16-bit star fields, so that's a pretty good compression ratio, pretty happy with it. But when we square root code the star field, it gets better. And that's for the reason I just mentioned. When you square root code, you're throwing away information that is random, the photon statistical noise. And as a result, the algorithm can work better on what's left over. That's kind of neat. So that gets us to an overall factor of 6, which gets us down to 13 gigabits per spacecraft per day of raw science data. And then we add various overheads to that, and that gives us some margin against our daily allocation. So pretty pleased with that. This is what we do on the ground. I'm not really going to talk about it except to say that it's very complicated. But I do want to call out one thing, which is this step here. At the very top here, we get raw frames off the camera, and at the end we have level 1 data, which are photometric images of the star field, like the very first frame you saw in that subtraction movie. One of the things we have to do is this PSF deconvolution. This is how our images are put together. this image was made from real data from the stereo mission. And as you can see, we've been careful to make sure our fields of view overlap so we can cross-calibrate our instruments, things like that. The problem is, it's really hard to make a good photometric mosaic from different parts of different instruments. We really have to understand the instrument performance. And in particular, instruments have a point spread function. An image of a star won't be a point, it'll be a little blurry shape. And that shape varies across the field of view. This has been a problem for some time. Over on the right is the seminal work that we found. It's from Kepler in 1611. And he's complaining about how stars change their shape in the telescope field of view. We had to translate Latin in order to find the right quotes. But it has indeed been a problem for a while. So we developed a mathematical transform that allows us to regularize the point spread function of the telescope. There's some math involved, convolution theorem, transfer convolution, things like that. The upshot is, this is, over on the left, a bunch of composite images of stars taken in different parts of the WiFi instrument field of view. And we're back into optics hardware rather than flight software here. But you can see those little tails. That's called coma. If you are an amateur astronomer, you'll see coma in different places. When we process that coma using, again, the Fourier transform and transfer deconvolution, we can regularize it to remove those effects. We start out with a star field that looks like this in the corner with these little tails all sticking out in different directions in different parts of the field of view. And we end up with a perfectly uniform, if somewhat out of focus compared to our best possible focus, star field. That allows us to overlay and compare across instruments, not just from overall flux, but from the actual imaging characteristics. We can produce a virtual instrument that is ideal. Very important. And of course, this is what data will look like. We're starting to simulate them. So this is an MHD model, a computer simulation of a CME leaving the sun that we processed through a simulated punch instrument. And this is what the output of the pipeline looks like. So you can see the CME propagating. So on that note, I will wrap up. We live in the outer atmosphere of a star. It's really cool. If you haven't thought about the science of the sun, it's a neat thing. And any mission that you work on is doing something cool, right? Flight software is not just something that you implement to get the job done. It enables really amazing things. We'll be imaging the sun starting in 25, so a little under a year. The flight software is integral to the mission being performed. I showed you a couple of ways where really subtle effects in flight software have really impacted science data coming from a mission. And so we really, for Punch, had to design the performance and structure of the flight software very carefully to try and meet the needs of this particularly precise mission. And the ways in which the impact can happen is non-intuitive. Sometimes things that you might just think of as business as usual can really have an impact on the mission. I will stop there. Thanks for your attention.
Oh, okay. All right. Okay, so we're going to do some Q&A. I forgot to mention this, that we have mics in the room, so we'll be able to ask from where you're seated. Also online, we have the Slack channel. So I'm going to ask you, Eddie, I know there was a question over Slack, and I couldn't pull it up right now. So that question is from Igor. Is Igor in the room or remote only? You had the question. Would you mind just go ahead and restating it, Igor? Your question?
First thing, congratulations. My question was about the downlinking and the strategy. You have answered. Thanks a lot. Kind of the data compression, the downlinking strategy. You know.
I'm sorry, I didn't hear it.
Okay, all right, let's do that.
I apologize. You were asking about the data compression stratlgy?
Yeah, you have already answered. My question was at the beginning of the.
Okay.
All right, great.
Sure. So yeah, lossless, but really we have to say quasi-lossless because we are throwing some things away. We're just in a well-defined way.
All right. Other questions? Okay, this question is from Greg Dunn.
So you have some known effects from flight software. Were there any discussions or about updating it to fix some of those effects?
No, by the time these were noticed, I mean, this is well underneath the requirements. The mission met its requirements. Just crazy people like me went in and tried to get the most we possibly could.
Oh, yes.
Hi, can you talk a little bit about the regularize PSF function a little bit more? Does that take into account spacecraft attitude, position, and velocity to back out the PSF, or how does that work?
Funny you should ask that. Let's see, I think we can go back to the math for a second. We are very fortunate that we have a built-in PSF monitor in the instrument, right? Because we're looking at a star field, and everything should look like a point. So if you're familiar with the Fourier transform, it does an amazing thing, which is it converts convolution, a point spread function operation, to pixel-wise multiplication. So if you Fourier transform an image that has a PSF applied to it, what you get is the Fourier transform of an image times the Fourier transform of the PSF. So that means deconvolution is just division. And so that's what we do. There's a little more to it than that. You can't divide by zero. It's only a semigroup, right? So we don't aim for full deconvolution to get down to points. What we aim for is convolution by a known PSF that is confined enough that it meets requirements, but worse than the actual optical performance of the instrument. And by making that compromise, we can get absolutely uniform performance all the way across.
That makes sense. Thank you.
All right. Any more questions? I'm going to check the Slack channels. No? Okay. Another question here. Please state your name, too.
My name's Jack White. Do you have any publicly available papers or anything on the things you've been talking about?
Absolutely. In fact, I had meant to put stuff on, and for scientific audiences, I usually do. But yes, I can give you some references.
Thank you. All righty. Yes.
My name's Josh. With optical comms coming online and being more prevalent, if you had better throughput, would you take some of the would there be benefit to take the risk away from flight software and just send raw data down, or do you still see benefit to putting it on orbit? The compression, the data processing.
I think it's a monetary question. If the passes get inexpensive enough, then of course you want to offload everything you can from the spacecraft. We're in an interesting place, right, where computing capabilities and FPGAs have gotten good enough that we can really put a lot of smarts onto a spacecraft. And so when you're designing a mission, it's really a financial question or a risk question, how much you want to put on the spacecraft versus how much you want to pay to transfer that stuff down. So optical comms will really change that balance, and we'll need to really rethink it, right? Yeah, it's a good question.
Chris Easton, I'm actually interested in, you open sourced the regularized PSF code base, and
how, like, we're a bunch of software engineers who want to share stuff with the world. Were you part of that decision making? Can you talk about what went into that at all?
Sure. As a scientist, I feel very strongly that our work has to be reproducible. And so I insisted that every piece of code that we can is open sourced. And so that came from the PI. And we're doing it via GitHub. So if you get on Google and search for regularized PSF GitHub, you'll find that. And it's part of a repository with every piece of analysis software that we've written. That's something that is often done piecemeal, but I think if more projects just decided up front to share what they can, I think we would all live in a better world.
Hello, Craig. The question I have is the average density of charged particles in the interplanetary space is always changing, and that's also related to the solar activity. And that, in turn, would affect the polarization and the scattering of light as well. So how would you mitigate effects like this? So, for instance, if you have a CME that's coming out, and then at the same time, you have more activity that's, like, say, some sort of particle acceleration, activity happening at the same time, which could be close to the event itself. How would that affect the observations?
Well, it's an interesting question. Maybe we should hit it afterward, but I'll address it briefly, which is Punch will be measuring the polarization of this light. I didn't talk about it, but it's to measure the 3D structure of the material. The 3D location of each of these features in the corona and heliosphere determines the degree of polarization of the light we're looking at. And so by measuring the degree of polarization, we can back out where that feature was in 3 space, just like with a stereoscope or something. So the question really is about how the polarization changes as a result of energetic particles and so forth. I think that is a scientific detail that you and I should hash out together. Sure. Thank you.
Okay, other questions? All right. One last time online. Do you see anything? Nope. All right.
All right. Thank you.
Yeah, again, thank you, Craig. Appreciate it. It's great to see you.